In any case, we are delighted to have Professor Roberts speaking today. Professor Roberts is Professor of Statistics in Department of Statistics in University of Warwick. He has been recognized for his research to many awards and distinctions. He's a fellow of the Royal Society. He's received the Royal Statistical Society's Guy Medal, Institute of Mathematical Statistics Medallion. Um, Rather than making my own words, I'll just use his FRS nomination because that does a great job of summarizing his contributions. And it reads as follows. Gareth Roberts is distinguished for his work spanning applied probability, Bayesian statistics, and computational statistics. He has made fundamental contributions to the theory, methodology, and application of Markov chain Monte Carlo and related methods in statistics. He has developed crucial convergence and stability theory, constructed a theory of optimal scaling for Metropolis Hastings algorithms, and has introduced and explored the theory of adaptive Markov chain Monte Carlo algorithms. He has made pioneering contributions to infinite dimensional simulation problems, including exact simulation of stochastic differential equations and inference in stochastic processes. His work has already found practical application in the study of epidemics such as avian influenza, foot and mouth disease, and I guess now in COVID modeling as well. In addition to all of this, he's just a great speaker to listen to. So we look forward to this. Today he'll be speaking on Monte Carlo fusion problem. So Gareth, the screen is yours.
Thank you very much, Sandeep. It's a great pleasure to be here. Thank you very much for that very kind introduction. So this is a body of work I'm going to talk about today, which is joint with Hongsheng Dai at the University of Essex and Murray Pollock, who's now at Newcastle University. I guess we've been working on this for a few years now, it's sort of developing in certain directions. And I'm sort of going to give a sort of a state of play of where the sort of project is at the moment. And as part of that state of play, I'll talk about one paper which appeared about a year or so ago, and another paper which we already have an early version of the preprint out, but actually there'll be a much better version out, hopefully within a month or two. It's quite an interesting problem that we're going to be talking about, which comes up in a number of different settings, and I'll try and motivate it briefly at the beginning, and then describe what I think our contribution to it is. Okay, so the two papers which I'm going to basically talk about, I'll talk about aspects of both of these papers, are the Monte Carlo fusion paper, which, as I said, we published in 2019, and then the Bayesian fusion paper, which actually is not actually completed yet, but we have an early version of the preprint out on the archive if you'd like to see it, although as I said there'll be a better version out fairly soon. And I'm going to sort of split things up into Monte Carlo fusion, talk about that for a while and motivate that, and then go on to the Bayesian fusion model, which is an attempt to bring the ideas of the Monte Carlo fusion and to make them more scalable and more robust to more complicated problems and larger problems of various types. Okay, so the problem is sort of simple to state, and it's a very common problem in sort of computer science and statistics today. We might be interested in carrying out some kind of inference. Well, it needn't necessarily be Bayesian inference, but for us, it's going to be Bayesian inference based on. I'm just going to change my. That's better. Yeah, based on combining subsets of the data. The data that we have for doing Bayesian inference may be perhaps separated onto separate cores for various reasons. I mean, one reason is that maybe the data set is so large that partitioning the data is inevitable in order to make it manageable. Another application, which I'm not going to say much at all about today, but it's one of the things that we're finding most interesting at the moment, is inference under privacy constraints, where perhaps we have a number of parties who don't trust each other and don't want to share their data, or maybe they're not able to share their data, and yet they want to combine their inferences in some appropriate way. How can you do that without violating any privacy constraints that you actually have. To do that, you need to do essentially separate analyses on the different cores and then somehow combine them in some way. And there are many other situations. I'll maybe briefly talk about a couple later on, where this kind of setup comes up, where we want to combine these kind of inferences. Okay. But one of the problems is that in Bayesian inference, typically what you get is a sample from the posterior distribution. And if you have different posterior distributions on each of the cores, then there's no sort of obvious way to combine samples from these different cores to give some kind of sample from the overall posterior distribution. And there are existing methods. There's actually quite a literature out there now, but pretty much all the methods involve some kind of approximation. And the sort of approximations that you get from these methods are often not the kind of approximations that are well understood. So it's difficult to somehow quantify what kind of errors you might be making by some approximations. And very much the aim of this work is to see how far we can push exact methods, or methods which have some guarantee of accuracy and don't have sort of systematic biases. So let's try and state that now in a mathematical way. We have a posterior distribution of interest F, and that can be written as some product of FC densities over a collection of cores. As I said, so basically the problem we're going to assume is that we have these samples from FC, and we want to somehow combine them. And if you just think about it for a minute, there's no obvious way of doing this. If you know other things about these samples, for instance, if we knew that each of the FCs was Gaussian, then there are sensible, consistent things that we can do. And there's a nice and very simple approach by Scott from 2016 called the consensus Monte Carlo method, which is actually very quick to implement and just uses kind of simple Gaussianity, which turns out to be exact when each of the FCs are Gaussian. But if we don't know that they're Gaussian, then this method is approximate, and moreover, not a lot is known about the extent of the approximation. But there's other methods as well, which are more complicated, perhaps produce better approximations, but are computationally more expensive as well. So we're going to be aiming to provide a method that's exact, or at least consistent in some sense. So the methods that we'll be looking at in the second part of the talk are very much based on sequential Monte Carlo. So they'll only be exact in the sense that as you get more and more particles in your sequential Monte Carlo approach, you get consistency to the correct target distribution. Second aim is we really want to make these methods scalable, since many of the motivations, not all of them, but many of the motivations for this kind of problem come up because you have sort of problems which are large in some sense, typically in terms of data size. We want to make the methodology as scalable as possible. Now, scalability means many things in this context. It could be scalable to data. It could be scalable to the dimensionality of the problem. And there are other types of scalability which may be relevant. So I'm just leaving that rather vague for the time being. I'm not going to talk too much about this, but one of the important things we want to do is to look at the robustness of the methodology. For instance, to incompatibility of the different densities. It turns out that, in real life, even though we may have, different data sets on different cores, these may not be sort of completely independently allocated to one core or the other. It's much more likely that there's some kind of systematic bias because of the way we've just chosen to order the particular data or the way it's being collected. And that can mean that the FC densities themselves can actually be really quite incompatible with each other. How is that going to affect the methods? And it turns out that they could affect the methods quite badly. And some of the methods that are being proposed in this area perform very badly when we have incompatibility. And then the other thing, which I don't think I'll say too much about today, but we've now got quite a few theoretical and practical results about this to give guidance for implementing the algorithms that we're going to talk about, because there's quite a few user specified parameters that have to be put into the method. So in order to make it sort of useful, we need to give some guidelines for that. Okay, so I'm going to start off with something which is a simple observation, which turns out to be fundamental to everything that we do. And it looks like something that's not obviously useful, but it will turn out to be something that we can use quite nicely via a rejection sampling approach. So recall we have the product form for FF. And what I'm going to do is I'm now going to introduce essentially a capital C, which is the number of cores, C plus 1 dimensional distribution, or DC plus 1 if we're in D dimensions. So this red density here, this red G density, has the following form. It's a product over each of the cores of each of the FC squareds evaluated at the XC, multiplied by this thing PCY given XC. What is that? Well, that PCY given XC is just the transition density of any Markov chain or Markov process at a particular time with station distribution FC squared. And then we divide that by 1 over FCY. Now this looks really rather obscure and not necessarily connected to our original situation, because we're talking about FC squared here, and there's no assumption here that we can get samples from FC squared rather than FC, although we might be able to do that. But a simple calculation says that, you know, given this C plus 1 dimensional distribution, if you were to integrate out CX1 up to XC from this, and it's a straightforward calculation you can do on the back of an envelope, you find that the marginal distribution for Y is equal to F. Okay, so this suggests that if we can actually simulate from this C plus 1 dimensional distribution, then all we need to do is just to take the Y value, and that will be what we want.
Gareth, there's a question. Would you be willing to take questions in between?
Very happy to, yes.
So the question was, is FC known, or is it black box access?
Okay, so what's known about FC is that we can simulate from it. So we actually have samples from it, but it will turn out for the rejection sampling algorithm that we have to implement, we will need to at least know more about FC in order to carry out a rejection sampling for each of the cores, although that particular calculation can take place on that core and doesn't need to be sort of centrally done. So initially, we just need to basically know that we can sample from it. And certainly we don't need to know anything like normalization constants. So we're in the usual kind of Monte Carlo situation in terms of that. Okay. So yeah, so the marginal distribution of Y in this situation is equal to F. But how can we use that? There's a number of problems to this. I mean, one of the biggest problems is that even if we can find a suitable Markov chain which has station distribution F squared, we may not have tractability of this transition density that we actually have in G. And moreover, the density that we write down G here offers no obvious way to simulate it. You know, there's no sort of nice kind of factorization or decomposition that allows us to simulate from G directly. But it turns out that it's quite useful, and this is what we'll be working with. And it will turn out to be natural for us to use PC Y given X to be the distribution, the density of a Langevin diffusion which has invariant distribution F squared, FC squared. Okay, there are many other things that you could do, and we've tried various other things. This seems to be the most natural one so far, but that doesn't mean to say that there wouldn't be other choices that we could do. Okay, so the double Langevin diffusion is given by the displayed equation there. dx is equal to the gradient of log f dt plus dwt. So we're certainly assuming smoothness, at least that f is once continuously differentiable or once differentiable. Here, w is just a Brownian motion. And of course, it's well known that an invariant distribution of this particular diffusion is equal to fc squared. And from now on, we'll just essentially assume that we're going to use a density of this form. But there's a problem with this because, of course, the transition density of a one-dimensional diffusion, we know a lot about it, but it's not explicitly known. So we can't just sort of plug it into a formula for G, for instance. But one advantage of PC is that we do have some very nice representations for PC. In particular, I haven't actually written it down here because it's quite a long formula and it will sort of come up later. But there's a very nice representation for PC known as the de Guinna-Castella formula, which expresses PC in terms of the expectations of a functional of a Brownian bridge. And because of this nice expectation, it turns out that we can turn this into an algorithmic form and use it to solve our problem. So how's that going to work? Okay, so what we want to do is we want to simulate from G, and G is complicated. We can't simulate from it directly, but it turns out that we can do a rejection sampling algorithm and simulate from this H density instead. So H is a density on the same space, C plus one dimensional space. What is its density now? Its density is now in a much more sort of amenable form for simulation because it's the product over each of the cores of the FC x's, no longer FC squared, it's just FC now, multiplied by some kind of Gaussian term. So it's trivial to simulate from H if we can simulate from the core, from each of the FCs. Because all we need to do is to simulate from the cores independently, and then given that, to compute this, y variable according to a normal perturbation of y about the mean value of all the x's. So I simulate the capital C starting values, I compute the mean of those values, and then basically compute a normal perturbation about that with a variance that looks like T over C. Now, I've actually introduced a parameter here, capital T. Okay, and T could actually, I can choose T to be whatever I like, but the choice of T will be quite critical for the efficiency of the method when we end up doing things.
Gareth,
Okay.
the question is by Devavrat, is bar x the mean of xc?
Yes, so yeah, yes. So the bar x is the mean value of all the xc values. So the mean value of the observations that we get from each of the capital C cores.
Right.
Okay, so that's I think something we can do. Okay, so what we're going to do is we're going to do an accept reject algorithm. I'm going to simulate from H, and I'm going to accept with the probability proportional to G divided by H, and I'm going to hope that it works. Well, if you do some algebra and we use that de Guinna-Castella formula, then we have it turns out that we have a very nice form for this. Oh, this is just to emphasize, yes, before I get onto the rejection sampler, this is just to emphasize, this is the H density. Simulating from H is very easy. I simulate the X's from the FC's, and then I compute the mean value of these, and then I compute Y to be some normal perturbation of that. Okay. It turns out that there are some other choices of H which are more natural and can be more efficient, although they're somewhat more complicated. But if I do this, if I simulate from this H density, I'll need to accept with the probability proportional to G over H. And it turns out that this proportion, this ratio is proportional to two terms, a product of two terms, which are both less than or equal to 1, rho and sigma squared. What rho is it's just e to the minus capital C, the number of cores, times sigma squared over 2t. And and sigma squared is essentially just the empirical variance of the observations from the capital C cores. Okay. So, and then Q is something rather more complicated, which I'll talk about shortly. But let's just look at rho for the time being. Clearly, if I wanted to do an accept reject using rho and Q, I could separate them and say, actually, I'm going to have two accept reject steps, and my observations need to satisfy both. Well, in the rho accept reject step, I can make the rho step as good as I possibly can by taking capital T very large. So that this probability gets very close to 1. Although the problem with doing this is that then we have subsequent problems in Q. So actually, capital T, if I take T too small, then it will turn out that the rho accept reject step has a very small probability of acceptance. So there's not kind of an optimization for capital T, and I'm not going to talk too much about how you do that optimization, but we have some guidelines and some theory supporting it in the paper. Okay, so there's a two-step acceptance probability. Rho is one step, and the second one is Q. And Q is somewhat more complicated. And what Q turns out to be is a product of capital C terms. And each of these T terms is a term that's very specific to the particular core that you're on. So we have an accept reject for each of the cores. And what is this? Well, so it turns out because of this de Grüner-Castello formula, I can write down each of these individual acceptance probabilities for each of the cores as the expected value of an exponential of an integral along a Brownian bridge, which is tied down to start at the starting value for that particular core, which is xc, and to finish at our proposed finishing value y. And then we have this functional inside. So we have a functional inside that's integrated between times 0 and capital T along the Brownian bridge. Okay, so the function phi just happens to be the Laplacian of fc of the density divided by fc. So the question before about what we need to know about FCs, this is a computation that needs to be something that can be done locally within each core. Okay, and we have also some constants which we've introduced, which are arbitrary, these capital phi's here, phi c's, and they're chosen just to enable that the integrand is always negative. Which ensures that we always get a probability for these accept rejects. There's quite a lot to take in there. It's much easiest to see that in terms of a diagram. What we need to do is to perform capital C independent tests, one for each Brownian bridge. And this is the picture that you actually get. So the Q rejection step. So given the starting point, so you can see the capital C starting points at the beginning, I just have 5 of them here. Given that, we can construct this terminal proposed point Y, and then we have a Brownian bridge for each of the cores that runs in between the starting value and the common terminal value. Okay, so in order to accept this path, we need to accept along each of the capital C paths. So there's C tests to be passed there, and also, of course, the rho rejection step has a further accept reject. So there's C+1 rejection steps that need to be passed in order for us to accept this as a simulation from the red G density. Okay, so how do we do this? So the step of this, which is going to be the hardest to do, is to actually simulate from events of this probability. We want the events of the probability, the exponential of this functional that we actually had along the sample paths of the Brownian bridge. Now, it turns out that we can do this relatively efficiently. Quite surprisingly, we can do this relatively efficiently using a methodology called path space rejection sampling, which I worked on about 10 to 15 years ago. And this is a methodology which involves kind of filling in some, but not all of the Brownian bridge in order to produce an event of a probability given by this quantity without bias. So it doesn't use any kind of discretization bias or anything of that kind. It's a method that turns out to be exact. I'll give those references at the end if anybody's interested, but it turns out we can use that methodology as a black box reasonably efficiently, except for one thing, that the methodology doesn't work for high dimensions. So the scalability in D for the dimensionality of the problem is something that's is a problem for path space rejection sampling. Okay, so just summarizing the algorithm overall, once we've got our starting points and our common endpoint Y, we propose these capital C Brownian bridges, and then we have an acceptance probability rho times Q. Rho essentially just looks at the C initial points and penalizes when we have too much discrepancy. And Q penalizes all the C trajectories according to some state-dependent hazard rate along the trajectory. And that uses the path space rejection sampling methodology. Okay, I'm just gonna, this is a very simple toy example, but I just wanted to sort of go through it just to sort of show what you might do. So this is a one-dimensional beta density, and I'm transforming it to the real line because these methods work best on the real line, and or on R to the D. So we get that density for X, and I'm just going to split it into capital C different densities just by taking the capital C root. So in this case, all the densities are identical. I can pretend that I can simulate from the FCs. In this particular toy example, actually simulating from the FCs may be even harder than simulating from F, but I'm assuming that I can do that. And then I carry out the steps of the algorithm as described. And just to give the results of this, which I think are kind of interesting only because the sort of simple approximation, the consensus Monte Carlo method of which is very popular, really gives quite a substantial bias for this simple toy example. The Monte Carlo fusion method is given in blue, and the sort of exact, since this is just a beta density, we can do everything exactly, of course, is given in black, and they're obviously giving the same answer. So that's interesting because even in such a simple example, I mean, obviously it's not looking anything like a Gaussian density, but in this simple example, we're getting quite a substantial bias for a sort of off-the-shelf approximation that's heavily used. Okay, but we need to be very careful because this method is going to have serious problems in scalability. So the acceptance probability of the accept-reject steps can be very small, especially when capital C is large. Remember, we need to do a step for each of the cores, and also when D is large. We've also got this tuning parameter capital T. Now, capital T has to be reasonably large in order to make the rho acceptance probability not too bad. However, if we take large T then we need to run these Brownian bridges over a longer time period, and that results in much higher probability that they will produce a rejection. So we've got a not very nice optimization in T, and there may not be a very nice sweet spot in the middle where you have efficiency. So it turns out that we don't have very nice robustness here. And one thing I haven't mentioned on these slides is another type of non-robustness, which is that if you have discrepant target distributions on each of the cores, if each of the FCs are quite different, then in order to make the row step reasonable, I need to make the capital T extremely large, and then of course that will produce further problems for the acceptance probability in the Q step. So this method, even though we like it, and in some sense it's the pure method on which to build things, it does not have good scalability properties.
So Gareth, we have a question from Chaman. He's worried about the dimensionality issues. So is there a dimensional threshold? Example, this method can be reasonably good up to a dimension, may not be that good after the dimension. What is the criteria this is true?
Yeah, so that's a good question. So certainly, I mean, if you have if you have a problem that's beyond, it's not as simple as a dimensionality issue, because it does depend an awful lot on the diffusion that we use and the shape of the densities that we have on each of the cores. However, in its pure form, the path-space rejection sampler is not going to work well in dimensions bigger than 100. And really, to make it work, very well and be very efficient, we're talking about dimensional problems, which are probably sort of less than 20. So that is a sort of, that's a serious restriction, but it still allows you to do it still allows you to do the exact method in that case. Okay. I dare say there are problems in dimensions above 100 that we could do, and there are improved proposal mechanisms which don't use Brownian bridges but use other types of bridges which could be used in particular cases. But I certainly wouldn't want to advocate this as something that you'd use in very high dimensional problems. Okay, so our aim is to construct a more scalable version, at least for the problems apart from the dimension scaling, which, as I said, is something that there is an intrinsic bottleneck in the methodology. Okay, so this is again talking about the method we just talked about again, but we're just going to critique it further. This is what we do. We start off with our starting values, XC, and we carry out a row rejection step, and then we get a common terminal value Y, by just taking the average of the X's and then doing the Gaussian perturbation. Then we construct C Brownian bridges, and finally we carry out the Q rejection step. So as we've just been discussing, this blue step is generally the limiting factor. Okay, so one of the reasons it's a limiting factor is that we need to actually we need to actually do this rejection over a time interval of length capital T, and we'd like to be able to split this up into kind of smaller subintervals. So what suggests itself here is a sequential procedure. So sequential Monte Carlo is ideally set up for doing these kind of problems. But the problem is that this is not set up as a sequential method as we currently start off with, because we start off with the X's and then we have a terminal value Y, and then we have to fill in the bits in the middle. So it's not set up to be in a natural sequential way, because we have to simulate the endpoint before we actually step through the different time steps. So steps 3 and 4 are not sequential, but the nice thing is that when we've got condition on our starting values, these XCs, which are certainly not Gaussian, But given that everything else in terms of steps 3 and 4 are just Gaussian. So we have a sort of Gaussian process here, conditional on XC. And so therefore there's some hope that that's going to be tractable and that we can actually find some sequential way of doing this. So this is a way of, so there's some nice calculations, and it turns out that a different way of writing these Brownian motions, which are interacting in this way, is to write it as an SDE, a forward SDE in the following way. I'm pretty sure this result must be known. I tried to sort of find it, but it's just kind of a nice kind of neat way of writing this. And it looks very much like the form for just a simple Brownian bridge, right? Except apart from having the terminal value y in the drift, we have this x bar. So what this SDE is doing is at any particular time t, it's computing the mean value of the particles, and then it's shrinking each of them towards the mean, with a drift which is getting larger and larger as we get closer to the terminal point at which they have to be equal. Okay, so obviously now we have a Gaussian process, we have an SDE, so it's now basically a forward process. I can now write it as, I can therefore write, it turns out that I can write down explicit finite dimensional distributions for this, and in particular the increment distribution of this, and therefore I can use this sequentially without any kind of approximation error. So that's what we do. So we're going to therefore be doing things forward. We're going to be, if I go back to my previous slide, essentially what we're going to be doing is we're going to be combining steps 3 and 4 into this common forward SDE approach, and then we're going to be constructing a sequential Monte Carlo procedure as a result. Okay, so to do this, if we want to use sequential Monte Carlo, it's natural to actually have a partition in time. And choosing the right partition is, again, something which involves some tuning parameters, which you have to be careful about, otherwise the algorithm will become pretty inefficient. I'm not going to talk too much about that, but as I said, we do have some guidelines for that in the paper. But for now, just construct some kind of discretization of time. And then we do an iterative treatment of the Q step. So with this, here's the Q step by breaking up each of these acceptance probabilities into much more manageable ones over the time interval between ti minus 1 and ti. Okay. And then the nice thing is that we can use path space rejection sampling, except not using it in the rejection sampling way, but use it in a weighted sequential Monte Carlo way to put this into a standard SMC framework in order to carry out this rejection step efficiently. So once we've got a time discretization, once we've got these acceptance probabilities broken down into the different time subintervals, we can actually construct a standard SMC procedure. It's standard, but the inputs that go into it are rather more complicated than most SMC methods. I'm not going to describe SMC here and the sort of the details of the formulae that you use, but essentially it's putting together the frame that we've just got in the sequential way with the standard SMC kind of machine. And basically how it works is we start off with a population, maybe quite a large population of C tuples. Okay, so each one has to pass the initial row acceptance probability test. And then what we do is we move these C tuples forward. Each of them has a weight. We move from time tj minus 1 to time tj according to the appropriate normal distribution. And then we use a resampling procedure to essentially duplicate the most important C tuples and to delete the the ones which have negligible weight, and thereby concentrating the Monte Carlo effort onto kind of particles which are going to matter. Okay, this is the standard SMC way of doing things, and massively improves the efficiency, and in particular it allows us to choose capital T values which are quite a lot larger, because the rejection probabilities are not too well. The rejection probability is still in principle large, but because we're using this sequential Monte Carlo procedure, things are much more efficient.
Gareth, quick question for you. These time steps, can they be optimized or?
Yes. So we have some theory about how you should do the optimization for this, and it's quite it's not the sort of, we don't have sort of clean results which say yes, this should be exactly what your time step should be. But yeah, we do have some kind of guidelines and some theory which supports that guidelines to do with how the effective sample size of the sequential Monte Carlo procedure evolves between time steps. In other words, we choose a time step which stabilizes the reduction factor in the effective sample size of the SMC. And by doing that, we can make things stable in the SMC sense. So from the SMC sense, that's something that's known to give you efficient schemes. And it turns out, because of the asymptotic properties of these exponential integrals that we're using in the path-based rejection sampler, it turns out that we can do some maths on that to actually find out some guidelines. Okay, but I'm not going to report on that now because it's quite a complicated other story. But yes, we do have some guidelines about that, but it's not definitive stuff. We don't have sort of exact results that say you should always use this particular one. But we think we have methods which are robust and allow the method to work well.
And the fact that in the last discretization, the drift blows up, does that cause problems at all, or?
That's a really good question. Yes, that's a really good question. So there are some endpoint considerations, and to be honest, I can't remember exactly what the issue is. It turns out you do need to do something slightly different near the end, but it's not too bad. The point is that you are using a discretization, and so you don't actually have to be arbitrarily close to the end. But there is a cost to the computing very near the end, but it's not massive. Yeah, so it's a really good question, actually. Yeah, if I had some slides on that, I would say a bit more about that, but I think that would be going off at a tangent. But that's a very interesting question. Okay, so this choice of algorithm parameters, we've just been discussing a little bit about that. I should probably move on a bit more quickly now. There are interesting questions there, and I think we have some good guidance available. I just want to run through, to finish, I really just want to run through some very simple experiments that we've done. I can't say that we've done absolutely huge numbers of experiments on all sorts of different types of problems, but we have done some more realistic kind of problems. So these are, this is just an illustration. In these illustrations, by the way, I've got two slightly different versions of the initial Monte Carlo fusion algorithm in red and black, and the difference isn't massive, but they're essentially based on what I was talking about in the first part of the talk. And what this is demonstrating is that if I kind of optimize the capital T for a particular problem, but I have more and more discrepant FCs, so F1 and F2 here have means which are minus mu and plus mu, and I'm just going to move them further and further apart, and to see how the computational cost varies. And it turns out that the Monte Carlo fusion is essentially destroyed by this method. This is logarithmic running time, whereas we get very robust performance for the Bayesian fusion method, at least up to 5.5, which is quite a reasonably large discrepancy here. So that's good. And a similar comparison in terms of number of cores. Interestingly, I mean, if you have very small number of cores, we found that, you know, for some problems anyway, the Monte Carlo fusion can actually be cheaper. But generally, for a larger number of cores, we have much more robustness for the Bayesian fusion approach, as you'd expect. This is a simple logistic regression model with just 2 parameters, I think. And what we're doing here is comparing to two of the methods in the literature. It's a very nice work by Wang and Dunson from 2013, the Weierstrass sampler, which produces the purple distribution, which is a reasonably good approximation to the true distribution, the black distribution. And the consensus Monte Carlo, which we've seen before, is producing really quite large errors, particularly on, in this case, the second parameter. But don't get everything for free. And here's another quantification. This is looking at the integrated absolute difference between the densities that we should get between the truth and the density that we get. Of course, these are, our method is Monte Carlo, so the answer would not be 0 anyway. But the blue is giving the errors that you get for the Bayesian fusion approach for a certain amount of computation. Purple got slightly worse for the Weierstrass sampler, and as you'd expect, much worse performance for the consensus Monte Carlo. But this is the sort of interesting thing is the consensus Monte Carlo is very, very quick. I mean, it's orders of magnitude quicker in terms of computational speed, which is illustrating. Whereas the Weierstrass sampler is also quicker than the Bayesian fusion in this particular example, but although maybe not appreciably so. This is on a real data example, which is again a logistic regression, and there's just 4 of the parameters, and we're seeing a similar story here. It's interesting. I mean, the method that we have seems to still sort of hug the true density. Since we're using a sequential Monte Carlo approach, of course, our method is not completely unbiased, and it's only going to be consistent as we get a large number of particles. And there is a suggestion that there is a slight bias even in the Bayesian fusion approach here. Again, I can do similar things in terms of the error analysis, which just confirms what we've seen. And yeah, that's and therefore, so the method can be used, and we have used it on now actually on more complicated examples. So it's interesting, and so we have a lot more to do, I think, on assessing, how the method performs in comparison to other competitors in other examples, because our initial analysis, I'd say, is on a rather sort of a limited set of examples, although so far the examples are very promising in the performance. I just want to say, so I did say I would talk about the Fusion project more general and say other things that we're doing. There's some really interesting stuff which a student of mine, Ryan Chan, is working on to do with using different values of this capital T parameter for different cores, which is a natural thing to do if for instance, you have some cores which have maybe a lot more data than other cores. So it turns out to be a natural thing to work on and can improve the efficiency of what we're doing. I mean, another work that Ryan's doing, he's looking at trying to improve the efficiency of these methods by changing the topology of how we do the combining between the cores. Okay, so what we've been doing in this talk has been exclusively looking at the left-hand side here, basically combining all the cores together. But there are natural strategies which are different, and this kind of binary tree structure on the right-hand side is something he's been looking at, and that can produce some very nice results, at least in some settings. Okay, and another direction which we're very excited about at the moment is this confidential fusion, which is also work with Louis Aslet. We call this the Confusion project, which confuses a lot of people. But I'm not sure it's a good name, but that's what we call it anyway. And the confidential fusion problem has a lot of kind of interesting kind of aspects. And the idea is that the nice thing about this, the whole fusion approach is that you can do so much this computation just locally on each of the cores, and then all you need to do is report these XCs and some of the decisions that you make, i.e. the accept reject decisions. And even some of the accept reject decisions you can actually treat confidentially using various kind of nice results from confidentiality. Okay, so that's basically what we're doing. We're also been working on improving the Brownian bridge approach using various things like Ornstein-Uhlenbeck bridges. And this actually has very interesting connections to the CMC, the consensus Monte Carlo algorithm. And there are other application areas in different areas, which I'm not going to go into now. And just to give some conclusions, I know there's some questions, but I'll give the conclusions first of all, just in case it covers some of the aspects. Okay, so this gives it a scalable, the Bayesian fusion method gives a scalable, at least to some extent, consistent methodology, which is robust to a sort of different distributions on each of the cores. It's not quite exact because it has SMC at its core, but it's consistent, and the consistency issues can follow from standard SMC. There are other things that you can do with this, in particular, if you really want to, and of course we would be worried about the scalability for large dimensional problems. There are other inexpensive approximations that you can do. For instance, you can completely circumvent the path space rejection sampler, which is the sort of bottleneck part of it. And you can circumvent that with an approximation, which would probably, we haven't really investigated this in great detail, but if this is done carefully, would give very competitive approximate methods, which would probably be competitive even for high dimensional problems with some of the sort of much quicker methods like consensus Monte Carlo. We have a sort of theory for scalability which is being developed, and we have quite a lot of results of this already, which will appear in the paper, which we hope to have out within a month or so. I have mentioned already that the path space rejection sampler is the limiting factor really for the methodology. And one thing I didn't say in the answer to the question before, there is a sort of a result to say that path-based rejection samplers should be order d squared in dimension d. So it's not impossible to hope that, you know, sort of it could be pushed to problems which are in dimensions bigger than 100, although we really haven't sort of gone there yet. But this is that result about order d squared involves optimization of the path space rejection sampler and optimizing all its parameters and everything working nicely. So it's feasible that we might be able to do things in somewhat higher dimensions, but certainly not in ultra high dimensional problems. Okay, and that's some references if anybody's interested, and I'd be very happy to also, if you have problems accessing any of those or want to see the preprint, which isn't quite out yet, then please email me later. So thank you very much for your attention.
Thank you. So Devavrat, do you want to just go ahead and ask your question directly?
Well, I was just wondering first if when you change the topology to the tree topology, would you still use the same algorithm, or would maybe you'd maybe a different algorithm would be better in that case? And
yes. So, well, what we've been investigating has been just essentially, essentially overall, what does the algorithm do? Is it starts with a sample from F1 and a sample from F2, and it combines them to a sample from F, right? So you can just essentially just iteratively apply that algorithm. But because the algorithm can often be very efficient when you do it for small c, and also the other things you can do is you can sometimes clump together the different cores which maybe have more similar densities, if you see what I mean. So you can make F1 and F2 more similar than F3 and F4. Then it may be very, very, very easy to combine F1, F2, and then F3 and F4, and then you've just got basically combining two later on. So there are various strategies, and we've investigated a few of them, and they do seem to, in some cases, give you some advantages.
Okay, any other questions? Right, I had a quick question. Now, in your third bullet point, you've mentioned that there are approximate methods which can circumvent this pathwise rejection methodology. Do they scale well with dimension, or do they also have dimensional issues?
So the purpose of those methods would be to completely circumvent the dimension. I don't think essentially what the path space rejection sampler involves having to do this rejection sampler on the very high on the d-dimensional space, there are lots of ways of doing it, but the limitation, the thing that gives you the d squared, how much detail do I need to go into for this? There's a step in the path space rejection sampler which is order d squared, and that could easily be made much easier using just a much simpler approximation. It's essentially just a step which simulates from a d-dimensional density which has some connection to the. I can't. How do I explain this? Well, the simplest version of that answer is just to say that there's all sorts of approximations that you could do, and the simplest approximations will certainly be scalable in dimension. How good the approximations will be is something that would depend on the context. But it's something that we haven't explored in great detail yet.
Okay, so if there are no further questions, then let's thank the speaker for a very nice talk. Thank you, Gareth. I'll just clap on everyone's behalf.